Swayam Prabha. Digital India. Educated India.
Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We both are from Civil Engineering Department, IIT Kharagpur. We have divided this course into two parts. The first part, Environmental Chemistry, will be covered by me, and the second part, that is Environmental Microbiology, will be taught by Professor Sudha Goel. I discussed in my module 1 the acids, bases and salts. In the second module, I discussed about the chemical equilibrium. In the third module, I discussed about the chemical kinetics. I elaborated the reaction rate, reaction order, how to determine the order, and how to use the differential rate law and integrated rate law to find out the order. This is my 17th lecture, and this is chemical kinetics, reaction mechanism, part B. You know that in chemical kinetics, the reaction mechanism is very important to know. Not only the order and rate, but we have to know how the reaction is going on, what are the steps that it is following, and it has some relation with the rate expression also, that we have to determine. This needs some knowledge also and some speculation also, that I will tell you. In this lecture, the content is the reaction coordinate and activated complex, reaction mechanism and rate determining step. I will discuss these topics here in this lecture. You know that one game we played in our childhood days. What is the game? That is the marble. We had some marbles, okay? And then we wanted to push the marbles. We wanted to cross that the marbles, means marbles cross a hill, okay? Hill, small hill, okay? And how we will do it? We will push the marble with sufficient energy, okay? Then the marbles will go up the hills, and then it will cross the hill and it will fall on the other side, okay? So, what we have seen, that when we push the marbles, then some of the marbles came back, okay, because the pushing was not so heavily, so not with so much energy, sufficient energy. So, some of the marbles will come back and some of the marbles will manage to cross the hill and to go to the other side. So, when one marble is going up, then the kinetic energy is decreasing, potential energy is increasing. When it is at the top of the hill, then potential energy is maximum and kinetic energy 0, and then when it crosses the hill, then again potential energy is decreasing, kinetic energy is increasing. So, this model actually can be applied here to understand the activated complex and how the mechanism is going to understand how the mechanism is going on. Here you can see that there is one reaction NO2 gas phase reaction, NO2 gas, carbon monoxide gas is giving NO plus CO2. This is a gas phase reaction. Now, here in the figure you can see that this is the energy, potential energy, and then this is the reaction coordinate. Now, these are the reactant molecules, these are the product molecules. Okay. Now, the reactant molecules, if actually when they will react, they have to come close. We all know that they have to come close with sufficient speed, sufficient energy, and they have to collide. Okay. So, we know that the reaction rate depends strongly on the molecular collision and the temperature, that I have explained in my third module, okay, when I told about the dependence of reaction rate on temperature. Okay. So, whenever two molecules will react, they have to collide, it is necessary they have to collide, but all collisions will not produce the reaction. Some of the collisions may not produce the reaction, only those collisions with having sufficient energy, they will produce the reaction, they will cause the reaction. Okay. Only those molecules with minimum threshold energy will be able to form the products. Now, what is happening here? The reactants come close, means they will collide to form an activated complex. Okay. They will collide to form an activated complex. So, they are colliding and they are crossing a uphill, that means they are crossing an energy state. This is the activated complex. Okay. And or it is also called transition state, which is having high energy as shown in the figure. Okay. This is the energy, that is from here to here you can see it is the ground state, these are the molecules, and then it has to have some energy, and then it will cross the energy, and then it will come to the product. Okay. Now, at this stage here, when the activated complex is formed, at this stage in this new entity, some of the already present bonds are broken and new bonds are formed. You can see here, because the reaction is between NO2 and CO2 form NO. So, here one NO bond has to be broken. So, this bond is broken and one bond has to be with oxygen, one bond should be formed between carbon and oxygen. So, here it is being formed. So, this is nothing but the activated complex or transition state. Now, activation energy of the forward reaction. So, when you consider the reactant is going to product, then it is a forward reaction, then the activation energy of the forward reaction is the energy difference between the activated complex and the reactant. So, this is the energy E for forward reaction. Okay. Now, the activation energy for the so reverse reaction is also possible. If you think about this NO and CO2 is going back here, then in that case from here to here it will go, and in that case activation energy is this one. So, activation energy of the reverse reaction is the energy difference between the activated complex and the products. So, this is very means it is not the same, but you can visualize like that marble I told you just now. Now, reaction mechanism, I told you that reaction mechanism is very important to know. It is also under the chemical kinetics, it is the under the scope of chemical kinetics. To ascertain the reaction mechanism, what we have to know, I already discussed in the previous lecture, that elementary reactions we have to know, we have to propose, or we have to write. Okay. We have to think a series of elementary reactions, because most of the reactions are not occurring in a single step. Okay. And when you consider the elementary reaction, you cannot think anything. Okay. You have to think the elementary reaction such a way that the overall reaction lead, that after combining all the elementary reactions, overall reaction you should get, and then you should get what is there as reactant and what is there as product, you have to match with that. Okay. not like anything you write and you add up, not like that. The reactant and product should be in matching with this proposition. Okay. Now, we may have several reaction mechanism, each of them is consistent with the overall reaction. So, for example, you have several mechanisms, you have written several possible mechanisms, then which one will be the correct one? One of the goals of chemical kinetics is to use the observed rate. So, you have to match with the rate also. Okay. So, you have several possible mechanisms, but then next you have to think about the rate. Okay. So, for example, this is one reaction that is written again NO2 plus CO, NO plus CO2, this is gas phase reaction. Now, the suggested mechanism consists of two steps. So, in the first step what is going on, NO2 is giving NO3 plus NO, this is the first step. Then second step, NO3 plus CO is giving NO2 plus CO2, second step. Okay. And this is the intermediate. Okay. NO3 is not there in the actual reaction. So, if NO3 is produced, it has to be consumed also, it is the intermediate. In between it is formed, but it should be consumed. Okay. So, here it is consumed. Now, the overall, if here only two steps are shown. So, overall by adding up you should get back this, okay, actual reaction, actual reactant and products you should get. If we combine the two steps and cancel the intermediate from the combined reaction, then we get back the overall. So, when you propose something, when you write some elementary reaction, a combination of elementary reaction for actual reaction, then you have to keep this thing in mind that you may produce some intermediate, but intermediate should not be there anymore in the balanced equation. Okay. It should be consumed. Now, an intermediate is a species that is formed and subsequently consumed during the steps. It should not appear in the overall reaction. Sometimes they are very short lived. Now, you may tell that only I am thinking, okay. Then how to prove it? How to prove? How to tell that okay, really this intermediate is produced? I told already that proposition of mechanism is difficult. You need lot of experiments also to do. Now, if you want to see the intermediate proof that this is formed, then you have to have some instrument, but sometimes the intermediates are so short lived, means transient existence, that it is very difficult to observe them. Okay. There are very sophisticated instruments also which can detect those short lived intermediates also. Okay. But here I am not discussing that. Now, reaction mechanism and rate determining step, this is a very important thing, okay, for reaction mechanism, rate determining step, I will tell you. Okay. In catalytic cycle there may be many steps. In a catalytic cycle, when there may be many steps, I already told you that in any reaction there are many steps, elementary reactions, those are called elementary reactions. Now, the experimental reaction rate is not the average rate, the overall rate is not the average of the or the cumulative of the rates of the steps involved in the reaction. Okay. So, rate of the overall reaction will reflect which elementary step, that is important. Rather, it is the rate of the slowest step, that I told you just now in the previous lecture, that slowest step is very important in the cycle, slowest step. So, I am giving another example to make you understand in a better way. So, for example, there is one file, I want to send one file with particular documents to one person, okay, high authority person. Okay. Then say for example, to go there, this is the 10th table. Say for example, I want to send my file for table number 1 to table number 10. Okay. Now, in between there are many tables. Okay. So, it will go from 1 to 2, then 2 to 3, then 3 to 4, like this, ultimately it will go to table number 10. Now, say for example, all tables, the person who is sitting is very fast. Okay. They are very efficient and they do it very fast, but one table is very slow, means person is slow. So, say for example, the file reaches there within very short time, and say for example, that table is table number 5. So, to go to table number 5 via table number 2, 3, 4 like this. So, it takes maybe very less time, say 2 hours time, and then from table number 5 to table number 6 it takes a 10 days. Okay. Then again after 6 table number 6 to go to table number 10, it takes only 2-3 hours. Okay. Then ultimately it is taking 11 days. Okay. But main time it is taking that table number 5 to table number 6. So, that is the slowest step. Okay. That is taking maximum time, that is the slowest step, that is nothing but the rate determining step. So, if you consider the overall thing to for the time taken to go to table number 1 to table number 10, it is taking only 11 days, but maximum time is taking there from table number 5 to 6. Okay. If you really want to expedite the process, means want to make it faster, then you have to make the faster the table number 5 to 6. Okay. That is the rate determining step. Actual rate is governed by that one. Okay. So, rather it is the rate determining rate of the slowest step in the cycle. Okay. In many reaction mechanism, one step is significantly slower than all other steps. This slowest step is called the rate determining step. But here in the reaction, in case of reaction, it is very important, not like that file. Okay. Here it is very important. If the rate determining step is first one, then analysis is very simple. Okay. Just by an example I can tell you. Okay. As for example, this is a reaction NO2 nitrogen dioxide plus fluorine gives NO2F. Okay. This is the balanced equation. Okay. Now, experimentally it is found that the rate expression is nothing but rate equals to K observed into NO2 concentration into F2 concentration. So, if this is one step reaction, then it should not be like this. Now, you know how to develop the rate expression. So, if it is not like this, then we have to find out some mechanism for this, how to speculate the mechanism, how to think about the mechanism. Okay. So, we can think about the possible mechanism for the reaction as NO2 plus F2 giving NO2F plus F. This is a slow process. Okay. This is the first step and this is the slow step. Okay. Here it is written that if the rate determining step is the first one, the analysis is simple. So, here the first one is slow step. So, analysis is simple, and the second step, this is the intermediate. So, it should be consumed. So, another molecule of NO2 is reacting with F to form the NO2F. Now, overall reaction, now it is matching 2 NO2, here 2 NO2, F2, it is F2 and 2 NO2F, it is matching and F is cancelling out. So, this is our speculated mechanism, and if this is true, means if we have thought about a correct mechanism, then the slowest step is the rate determining step. So, according to this, what should be the rate expression? It should be rate is K observed into concentration of NO2 and concentration of F2. So, it is matching. Here the first step is slower than the second step. So, first step is the rate determining step and following the same experimental rate expression, and the second step does not affect the reaction rate. So, here you see it is a simple case, but when there are a series of steps, then it is not so easy to tell about the mechanism. Okay. Now, reaction mechanism and rate determining step. Okay. Mechanisms are more complicated when the rate determining step occurs after one or more fast steps. Okay. It is not the slowest step, previous one was slowest step is the first step, but here it is not like that. Here what is happening, slow step more complicated when rate determining step occurs after one or more fast steps. So, for example, this is another reaction 2NO plus O2 giving 2NO2. Okay. So, here rate expression it is observed that rate is K observed NO to the concentration of NO to the power 2 into concentration of oxygen. So, you can tell that okay, it is matching with this. Maybe this is a one step mechanism, okay. But we have already discussed that single step thermomolecular reaction is not common. I already explained that it is not common. If we have other possible mechanism, we have to consider that. So, can we have some alternative mechanism, alternative pathway? Can we think? At least we can think, okay. This would be consistent with the form. So, how to think? This would be means thermomolecular, if it is thermomolecular mechanism, that it will match with this rate expression, but it is not common. So, can we think an alternative pathway? Let us see, let us see whether we can do it, okay. Now, an alternative pathway we can think in this way: NO plus NO is giving N2O2, this is again an intermediate. So, it is a fast equilibrium, okay. This is the first step and this is a fast equilibrium, okay. So, if it is an equilibrium, then we know how to develop the equilibrium expression. So, K1 is the equilibrium constant for this reaction, and then for this step actually, and then it is nothing but N2O2 concentration by NO concentration to the power 2, okay, where K1 is the rate constant for forward reaction and K1, K minus 1 is the rate constant for the reverse reaction. Here it is not written, you can think this one, K1 is the equilibrium constant, okay. Basically K1 is nothing but K1 by K2, so I have not written that, okay. Now K1 is this one. Now we can just rearrange it. N2O2 concentration is nothing but K1 into NO concentration to the power 2, okay. Now next step, what is the next step? Next, because this is an intermediate, so it has to be consumed. So next step is N2O2 plus O2 giving 2 NO2, and this is a slow step, it is a second step, okay. Now we know that the slow step determines the rate, reaction rate. Now then what will be the rate? Rate will be K2 into N2O2 concentration into oxygen concentration according to this one, okay. Now here N2O2 is not appearing in the reaction, okay. What is the reaction? That let me show again. This is the reaction. This is the reaction, okay. So there is no N2O2. Now then what we can do? We can put the value of N2O2 here. N2O2 that we can put from here, okay. N2O2 is nothing but K1 into NO to the power 2, okay. Now after putting this, we are getting this. So this is a constant, this is also constant. So we can write that this is K observed, another constant, okay. Now if you see the rate expression, it is matching with the actual rate expression that experimentally found, okay, this one. So this alternative mechanism is not considering a thermomolecular reaction, but it is considering first equilibrium, this is the first step, then second step is the slow one, decomposition of this with oxygen, not decomposition, reaction of N2O2 with oxygen to form this one. It is matching, after combining it is matching with the balanced equation, as well as after considering the rate expression also we see that it is matching with the this is the obtained one, and it is matching with the experimental one. So maybe this mechanism is correct. So just I have shown that how we can think about a possible mechanism, what are the different things we have to keep in mind, okay, when we develop the elementary reactions, okay. Now so this is very important, you know, for mechanism, these are the general concepts. I have shown you with very simple reactions, okay, but actually the reactions are not so simple, they are complicated, okay. They may not involve 2 steps, they may involve more than 2 steps, okay. So and also some knowledge is required to think about the elementary steps, but at least we can think, okay. We know what is the elementary step, we know what is the balanced equation, we experimentally we can find out the rate expression, order of the reaction, everything, and then our thinking should comply with all those things, and it should match. Okay. Then only we can tell that okay, and also possibly sometimes we can determine the intermediates to prove that okay, our speculative mechanism may be all right. Okay. Now, these are the different things we have to consider. Rate determining step is very important to get the concept. Okay, very important. The concept of rate determining step, intermediate, all those things are very important to write the mechanism of a particular reaction. Okay. Now, these references you can especially this book is very nice explained. Many of the examples I have taken from this book, and very nicely explained. You can read, if you can get this book, you can read it, and this book is also good for this mechanism purpose. Mainly this book is very interesting and important. Okay. Now, as a conclusion I can tell that it is very important to know the mechanism of a chemical reaction. Very important to know the mechanism of a chemical reaction. One of the goals of chemical kinetics is to determine the reaction mechanism from the rate expression obtained experimentally. Okay. In many reactions, one step is very slow compared to the others. The slowest step is called the rate determining step. Okay. So, these are the main things that I have covered in this lecture. Okay. And possibly you can try to develop some elementary reaction for a particular balanced equation, and if you know the rate expression, then you can match with that. Thank you.